Hello students. In the last session, we have studied about behavior of a bar magnet when it is placed in an external magnetic field. In this session, we will be studying about origin of magnetism. Now when we look around, we see that only few materials can be magnetized. What makes some material behave like a magnet while others don't? To understand this, we must consider the building blocks of the materials, that is, atoms. An atom consists of positively charged protons and electrically neutral neutrons present at the center called as nucleus of an atom, and negatively charged electrons revolve around the nucleus of the atom. You must have studied in the periodic table in chemistry in class 11 that chemical properties are dominated by orbiting electrons in the outermost orbit of an atom. This is also applicable to magnetic properties of an atom. Let us consider an electron revolving around the nucleus in a circular orbit. An electron revolving in an orbit is equivalent to a tiny current loop. Consider the electron to be revolving in clockwise direction. Current I will be produced due to the electrons which will be in opposite direction, that is in anti-clockwise direction. We know that moving charge leads to production of magnetic field. Over here, the electron is a charged particle and is moving, so it will lead to production of magnetic field. The magnetic dipole moment due to current loop produced by orbiting electron is denoted by m orbit bar. It is a vector quantity and its formula is m bar is equal to Ia, where I is the current produced due to orbiting electron and A is the area of the loop. This magnetic moment, which is produced by orbiting electron, is called as orbital magnetic moment. Its direction is given by right hand thumb rule. If the fingers of right hand are curled in the direction of the current I, then the thumb shows the direction of orbital magnetic moment. Over here it is in upward direction. Electron along with the orbital motion around the nucleus also possess intrinsic spin. The magnetic moment produced due to intrinsic spin is called as spin magnetic moment and it is denoted by m spin bar. The total magnetic moment of the electron is given as m bar is equal to m orbit bar plus m spin bar. So the total magnetic moment m bar is the vector sum of the magnetic moment due to the orbiting electron and also due to the intrinsic spin of the electron. Let us now derive an expression for orbital magnetic moment. We know the formula for orbital magnetic moment, that is m is equal to Ia, where I is the current and A is the area of the loop. We have studied the formula for velocity, that is velocity is equal to displacement upon time. When electron revolves around the nucleus, its displacement is equal to 2 pi r in time period capital T. From this expression, let us get a formula for time period. The formula for time period will be 2 pi r divided by V. Now the formula for current produced due to electron E is given as current is equal to charge per unit time. So charge on an electron we denoted by E and time period will be written as capital T. Let us substitute this formula of time period into this equation for current. So I will be equal to EV upon 2 pi r. We also know the formula for area of the loop as pi r square. Let us substitute all of these formulae in the expression m is equal to Ia. We already know the formula for I, and we have also derived a formula for area. So let us substitute both of these formulae in this expression. We get it as EV upon 2 pi r multiplied by pi r square. In this equation, pi in the numerator and denominator will get cancelled out, and r in the numerator and denominator will get cancelled out, and we will get the formula for m orbit as EVR upon 2. This is the formula for orbital angular moment of the electron due to its orbital motion. So the magnetic moment which is produced due to the orbiting motion of the electron will be denoted by m orbit, and its formula is EVR divided by 2. E is the charge on the electron, V is the velocity of the electron, and R is the radius of the loop. For this orbiting electron, the angular momentum is denoted by L. We know the formula for linear momentum denoted by P, that is P is equal to mv. Similarly, if the object is moving in circular motion, its momentum is called as angular momentum, and it is denoted by L, where L is equal to mvr, where me is the mass of the electron, v is the velocity of the electron, and r is the radius of the loop. Now we will find the formula for orbital magnetic moment in terms of L, that is angular momentum. We have derived this formula for orbital magnetic moment as m orbit is equal to EVR divided by 2. Let us multiply and divide by the mass of the electron, that is multiplying and dividing by me. After rearranging the terms, the MEVR can be written as L because we have seen that the formula for L is MEVR. So instead of MEVR, we write it as L. Terms E and Me are constant because the charge on the electron is constant and also the mass of the electron is constant. And we know that E is equal to 1.6 into 10 raised to minus 19 coulomb, that is the charge on the electron, and the mass of the electron is 9.1 into 10 raised to minus 31 kg. So we can write orbital magnetic moment is directly proportional to the angular momentum of the electron. So if the angular momentum of the electron increases, the orbital magnetic moment also increases. And if the